So this is our iLoad Pro load cell. It comes in either USB, UART, digital outputs, or we can give you a pigtail output like this at the end of the cable. So the red and black are the two wires on which you have to supply the power, which is 5 volts. And you can measure the analog output between the yellow and the black wires. And you'll get a 0.5 to 4.5 volt output when you apply loads on it. From zero load, it's about 0.5 volt to 4.5 volts at full load. So let's go ahead and power it now. So we'll use a standard power supply and use a 5-digit digital multimeter to measure the voltage. So as you can see, we have connected the two black leads together onto the black wire. The red is going to the power supply. We are giving exactly 5 volts, and then the other red is going into our voltmeter. And at no load, you can see that it's giving about close to half volt. It's never exactly half volt, close to it, about 0.55 2 millivolts. Now we're gonna go and use the Instron that we have, the machine that we have here that we use to apply known loads. This machine is calibrated to NIST standards and is traceable all the way back to NIST standards. So we're going to use this machine and our Blue Hill software to apply the loads. And we have a preset 2,500 pound profile set up to apply the load on this 2,500 pound load cell. We're going to press it in the compressive mode, so apply compressive forces, and then we'll see how the voltage changes. So the sensor has been set up for calibration. At 0 load, it is showing about 0.562 volts or 562 millivolts. This has been all set up to start the application of forces. So let's go ahead and click on this. So now the sensor is starting to be compressed. You can see the forces are going up here. The displacement of the thing is going up, and slowly now the thing is engaged and the forces are increasing. As it is increasing, can't see much here because it's like literally in the thousandths of an inch, but you can see here the voltage is slowly going up, and now it's showing about 1.58 volts, and that is because we have the first stop at about 625 pounds. So at 625 pounds, this is now settled at about 1.578 volts. So as you can see, the voltage has gone up from about 0.5 to 1.578. So similarly, now at the next step at 1,250 pounds, the new voltage is about 2.541 volts. And off it goes to the next stop. 1850 pound, 1875 pounds is a target. So now that we have reached 1875 pounds, the new voltage is 3.493. And the last step we take is at 2500 pounds, which is the full capacity. And now it's starting to go up. You can see the voltage is also going up. At full load, it should be close to about 4.5 volts. So it looks like it's reached that spot. It's 4.452, let's say. 4.452 at 2500 pounds. So we gather this data of load versus voltage, and then we provide a straight line fit like this. We do a best fit curve and provide a polynomial straight line linear fit that lets you measure the voltage and infer the applied loads by using this sensor. So after the calibration is completed, we generate a calibration chart for this particular unit that shows the applied loads and the output voltages for those applied loads. And essentially we get a linear number that you can use to infer your loads from the voltages which is shown here. So this is about 644.7 pounds per volt. So if you start out with your zero load voltage and figure out the delta from that number, you can just multiply it by this number and you'll get the applied pounds of force on your sensor. So this is what the calibration looks like, and that's what the calibration certificate that you get will look like. The one last thing I want to show you here on this one is that in addition to the pigtail that we provide with the load cell, we also provide an additional cable which lets you put this into the load cell here in place of the digital one, in place of the analog one, and then you can insert this, and then we also provide the serial to USB adapter at the end of the cable. So using this cable, you can use this sensor in the digital mode, in the USB mode, and you can also use it to recalibrate it and troubleshoot it if something comes up. So you can use the same sensor in digital mode or analog mode. And lastly, this is what we call the HX100 adapter. So if you didn't want to cut off the end of the connector and have a pigtail, as we showed for the analog cable, you can use this adapter and preserve the USB functionality. Here's a USB, here's a USB, so you can still do the USB, and you can tap into the analog output by measuring the voltage between the yellow and the black wires here. Also, if you want to go to an Arduino or some other microcontroller, you can talk TX-RX using this HX100. So you can go from UART into your own microcontroller directly from the iLoad Pro load cell. So that's how it works. So this is again our iLoad Pro load cell. We just showed you how to use it in either the analog mode or digital mode or universal. You can hybrid mode where you can get both digital and analog. So I hope you liked the video and you learned something from it. If you would like to use this in your application, please call us at 510-274-1872 or reach out to us via sales@loadstarsensors.com. Thank you.